Okay, so first of all, I would like to thank Mike for inviting me to watch over his program while he was off on his sabbatical. I've been handling his program since the beginning of the fiscal year, while he's been off at Yale and Santa Barbara and lately at Florida. I'd also like to thank his chain of command, Joan and Tom, for giving me this opportunity, as well as my chain of command. So I'm going to be briefing the molecular dynamics and theoretical chemistry portfolio. And let me start out by saying that the intent here is to be able to support research that allows us to be able to understand and take advantage of fundamental processes that are connected with chemical reactivity and energy flow in order to be able to understand and design improved materials, processes, and systems that are important for the Air Force and for DoD. And so an important component of this, and as you'll see a strong emphasis in this program, is to be really looking at catalysis as well as ways to be able to store or generate as well as utilize energy. So some of the sub areas are in the name of the portfolio, and here the first one is molecular dynamics. And I want to point out that our conception of molecular dynamics is one that includes experiments. We heard a lot in John Schmischer's talk that there are molecular dynamics simulations. So that's kind of one perspective that's really basically only theory. And as you'll see, there's a strong experimental component, and the other aspect is theoretical chemistry. So the sub areas that I've listed here are atmospheric and space, energetics, nanostructures, and catalysis. And this is sort of the breakdown that's a little bit different here, which is how I'll talk about the challenges in terms of what it is we're really trying to figure out, some of the payoffs in terms of the kind of materials and processes we're trying to improve, and the specific kinds of materials and processes that we're looking at to this end. So the first category is energetic materials. Here what we're trying to do is develop better explosives and munitions. And some of the things that we're trying to accomplish is to come up with new formulations that are beyond the limitations you have for standard organic materials that are composed of just carbon and hydrogen and nitrogen and oxygen. And here, a lot of the thing you're trying to do is get better yield, better performance, but at the same time, also engineer in less sensitivity so that they're safer. And the specific kinds of systems that we're looking at are energetic ionic liquids, nanostructures, and nanostructures really designed to have some catalytic effect. And this is something that I'll talk about. And another component is looking at nanostructures. And these were initially really pointed towards doing sensing. And really, this is something that we're really redirecting more towards looking at energy. And here, as I'll say more about, a lot of the trick is really being able to understand and take advantage of how the size dependence of small nanostructures can give you opportunities to be able to do new kinds of chemistry, especially when it comes to catalysis. And some of the other things we're looking at in this portion of the portfolio includes photoelectrochemical materials. And in this area, we're using plasmonics. Again, that's a case where initially those were really designed for looking at sensors, and they're transitioning to really trying to do chemistry in new ways. So other areas include atmospheric and space chemistry. We heard a lot from John Schmischer, who demonstrated that there's a lot of interest in being able to take things that have been studied for some time in terms of the physical chemistry community, in terms of energy transfer in the gas phase, and really helping to understand and promote development in hypersonic applications. Similarly, there's been work in terms of lasers and diagnostics, and especially in high-power gas lasers, there's actually a lot of understanding about energy transfer and things like that. And these are, again, being really mostly folded back into new ways to be able to look at things that are catalytic. So the scientific challenges here are ones that really are being able to have a good perspective, a good experimental view and theoretical understanding of sort of the complex nature of catalysis. So these are quite complicated systems that tend to be very heterogeneous. And as I'll mention, one of the unique aspects of this program is to take a lot of the tools and understanding from chemical physics and physical chemistry and really point them at getting a much more detailed understanding of these complex processes. So understanding and being able to control the mechanisms to be able to really guide the design of new materials. And a key component of this is that it combines different kinds of approaches that we're making new materials, using different kinds of simulations and also state-of-the-art kinds of experimental techniques to get a closer look at really what's happening at a real molecular level so that we can really understand how the interactions and the different classifications of materials can be understood to be able to promote a particular kind of activity, where a lot of the work here is really emphasizing what you can do with nanostructures. These are sort of well known to be catalytic systems because they've got a high surface area to volume ratio, but another aspect of them is that they've got unique behavior as you go from sort of an atom to bulk size regime. And this kind of catalysts, of course, are key for energy storage and utilization. They're important in a wide range of contexts, not just military, but also industrial. And these are going to be also used in different varieties for both energy production and utilization, as well as energetics. And so while there's some differences in these kinds of applications, there are also some similarities in terms of understanding what happens on different scales and looking at the mechanisms. So next I'm going to talk about some of the transformational opportunities, the kind of areas that these kind of studies can impact. One, we also heard a little bit from John talking about this idea of endothermic fuels. And this is a real cool idea. Actually, it's a cooling idea because it's a way that you can really thermally manage what happens in a hypersonic vehicle. And this is something that will allow you to really get better performance. And it actually does sort of double duty because really the way this happens is large hydrocarbons endothermically crack on the sides of on the walls of the engine, and that also makes the fuel burn more efficiently. And so this is actually the motivation for FY08 Muri that I'll have something to say about on nanocatalysis for propulsion. And it's also the topic for a Muri that's just been awarded this year in FY13, and the BAA is coming out or almost out. So the second area is when it comes to secure energy and power. And this has to do with investigating, again, emphasizing the importance of catalysts for producing some alternative fuels, as well as, again, being able to more efficiently take advantage of legacy or more traditional fuels. And in addition, there's a lot of work going on being able to come up with new formulations for propellants and energetic materials. These involve ionic liquids, and there's actually some exciting progress that's been made in this area that I'll also talk about. So I also wanted to mention, that energy is, of course, a very big area, and there's a lot of interest across, a lot of different agencies. And Mike certainly has a big handle on this and coordinates across these different agencies. Really, all I want to say about this is that some of the things that we're doing is to take advantage of some of the large laser facilities that DOE supports, and looking forward to getting these kind of facilities on a tabletop like Rick was promising us to be able to have. And when it comes to DOD, especially in the energy field, there's guidance that's been provided by the Energy Horizons strategic work that Joan talked about a couple days ago. And I think Mike and RSA in general contributed to some of the information that went into establishing that guidance. And some of that spells out that AFOSR is really emphasizing really fuel utilization and performance, even though to a limited extent really alternative fuel generation. And when it comes to energetic materials, there's a lot of cooperation. I certainly see there's several portfolios that are involved in energetic materials in RSA. And there's also good cooperation across different agencies. And something that's unique about AFOSR is that it's really taking sort of a physical chemistry approach to a lot of these kinds of topics and really trying to understand things at a detailed and fundamental molecular level. And so this brings me to sort of the program strategy here in this program, which, as I said, is one that really emphasizes a chemical physics approach. And so one way to think about that is to get detailed information, which is sometimes most easily obtained by looking at things that are isolated and for small molecules. And sometimes these play a role in these processes as reactants or products. But really, especially when you're talking about catalysis, what it means is to be able to make the situation closer to a practical system, which means to understand how to try to understand state-to-state kind of events as you start to change the environment to one that's going to look more like what you're going to see in a practical system. And in this context, this program and this approach is really well suited to being able to identify and take advantage of some of the unique behavior that you get for building up and systematically building up a material from sort of an atomic and molecular level to sort of the intermediate regime before you get to bulk. And this is where you can really get unique and catalytic properties that you can take advantage of. And some of the unique property or capabilities in this program are being able to develop tools so that you can really go in and see what's happening at that level in more practical systems. It used to be that we would have to strip away all the complexity to get detailed information, and now I think a lot of the progress that's being made in this area is to be able to look at things in detail under circumstances in which they're really going to be operating. And so that's something I hope to be able to convey. So this program is also comprehensive. As I mentioned before, there's a close coordination between theory and experiment. And it's systematic in terms of being able to come up with sort of what are the really fundamental tools that sort of cut across these different materials, and at the same time to be able to identify promising new materials and understand how they work, to sort of work that backwards to generalize it. In terms of the program trends, this actually looks very similar to sort of what Mike presented last year. I really just added a few adjectives here to what's happening with catalysis. As I'll say later, really what we're trying to do is come up with more sophisticated approaches to catalysis, more complicated structures, or maybe sequential or actuated catalysis. The rest of these are probably being maintained at about the same level. And as I mentioned, sort of in a flat world, when it comes to funding, if you're going to increase something, you sort of need to drop something out. And so there's a little less emphasis on sensors for detecting materials. And so we're folding in some of these sensing capabilities to get a better look at what's happening in the catalysis. So next I want to talk about some of the results that have been successful and transitioned. And I want to talk about some of the work that this is technology that's typically used in these kind of experiments where you can use spectroscopy as particle detection to get very high sensitivity and specificity. And this works really well in the lab, but this project that's being done at Special Technologies Laboratory, that's part of this National Security Technologies DOE lab, is one in which they're trying to shrink this mass spec, tandem differential mobility spectroscopy down so that you can actually carry it out into the field, so that you can have that kind of sensitivity in sort of a practical application where they're also combining this with atmospheric sensing. So you can bring the kind of sensitivity that used to be restricted to the lab to do sensing, and furthermore they're using this for nuclear forensics to look at isotopes of uranium. So next, let me talk about some of the results in the portfolio, where I'll start about talking about a recent MURI. This is a FY10 MURI on solar fuels that's associated with trying to do CO2 reduction for alternative fuel generation. This is the PI here is Cliff Kubiak, and sort of the two tracks I would say that they're sort of pursuing at this early stage. First of all is to come up with systematic approaches to being able to accomplish this task. So let me just back up and say that this is a solar fuel generation that in a way is an alternative to photovoltaics. In photovoltaics, you're harvesting energy and then trying to get it into electricity. And that's got some challenges. But also, in some ways, electricity is more difficult to store. It's easy to spill electrons. It's hard to hold on to them efficiently. And it's also not really, as Mike said last year, it's not what the Air Force actually uses to operate its planes either. So really, you'd rather get a fuel. So some of the approaches that have been recognized that they're looking at are maybe doing sequential reactions to be able to optimize different steps. These tend to be multi-electron reductions. And one of the things they're also doing is identifying mechanisms for being able to carry this out. In addition to that, a big component of this MURI is recognizing that there's a successful organic reduction catalyst that was discovered by Andy Bukharsley's lab in Princeton. And a big component of this MURI is to really understand the mechanism for how this pyridine-based electron shuttle that operates in the presence of gallium phosphide, how this actually works. So this photoelectrochemically has been shown to be able to reduce CO2 to methanol, and this also works electrochemically. And so being able to understand this will allow us to maybe improve on the system or generalize it and extend it to other systems. So one of the first results that I'm going to talk about is from Cliff Kubiak. And he was looking at these nickel cyclams, which were recognized to be efficient for this reduction of CO2. So one of the results that they found was that they thought that you had to have mercury present for this to happen, and it wasn't really clear why that was. And some of the calculations that Cliff did sort of gave him an indication of really why that is. And it's because this, the nickel is in sort of this ring that's got nitrogens. And in one of the conformations, all the hydrogens are pointing up. And this actually makes a nice kind of structure for being able to bind the CO2. And so based on the structures, he was able to figure out that probably what the mercury was doing was really just pushing this into the right structure, and that you don't really need the mercury. And he's really extending this kind of idea to other kinds of systems. This nickel, P2N2, is sort of a, you find this in the core of a very efficient formate dehydrogenase. And so he's sort of mimicking that and synthesizing it, testing it, and really understanding it in the context of hydride transfer energetics. So they're making very good progress on this system. Another person working in this program is Jens Norskov, and he's a world leader when it comes to really developing these volcano plots. I think he's the father of these volcano plots, which is the way that a lot of people look at catalysis. And so this is kind of intuitively appealing, which is that as a function of the binding energy, what you really want is something that binds strong enough that you can get it to react, but you don't want it to bind so strongly that it ends up being poisoned. So you sort of want something in between. And so he's looking at these binding and desorption kinetics for the system of copper. That's one of the ones that will actually reduce CO2 in the presence of water to hydrocarbons instead of hydrogen, and has been able to demonstrate that the rate limiting step is really hydrogen attraction to hydrogen interacting with CO. And in addition, I wanted to point out that he's got a application that you can go log on to that'll give you online surface-specific barriers, so that if you want to come up with how you're going to design your own experiment, you can sort of get started with some of the information there. So as I mentioned, another aspect of this MURI is to really understand sort of the mechanism for this Bocarsly reduction catalyst. When they started, it wasn't clear whether it was homogeneous, whether this pyridine was working like an electron shuttle with a carbamate intermediate to go to formic acid, formate, acetone, and then methanol, or whether it had to do with surface-bound species. It could actually be the presence of the surface, could have just been activating some species in solution. So this is something that Emily Carter took on to be able to at least look at the energetics of forming this active species that you think would be mediating this homogeneous mechanism. And she demonstrated by doing the calculations for the proton, the pKa for this activated complex, that the energetics really don't work out, that you're almost a volt away from really being able to do this at the voltage that it was experimentally observed. And this really gives very strong evidence that it's actually a surface-mediated reaction. At the same time, the Bocarsly group has been looking at this very successful pyridinium system and trying to see what other kinds of materials will work. They've recognized that imidazole works as well, and other surfaces, including gold and iron pyrite. And so this is allowing them to be able to sort of identify how the system is really working, expanding it to new materials. So next time I'm going to talk about a little bit older MURI. This is NanoCatalysis for propulsion. There are actually 3 MURI teams that are on this. And then there's actually another team that's funded out of Mike's core that's also working on it. So there's a lot of activity in this program. And as I mentioned before, this is really motivated by trying to understand and optimize the endothermal fuel for hypersonic vehicles. And so the objective in order to do this is this idea of putting materials in the fuel to be able to get them to crack and then to cool the engine. And this is something that really spans a wide range of different kind of phenomena, from things down at the small scale of understanding molecular mechanisms for some of the reactivity in terms of the catalyzing this cracking, as well as some of the more macro scale kinetics and mixing in order to get good performance out of these systems. And so one of the things I really wanted to point out is that that in this system they're really, I think, breaking new ground in terms of really being able to go in and look and see how you get different kinds of reactivity for different sized nanoparticles. And so they're taking real world catalysts and sort of deconstructing it, but still preserving a lot of the real important conditions that are needed to be able to follow what's happening in a real system, in these reactions. They're doing reactions and very detailed size-dependent studies. And sort of this is intended to show the different kinds of knobs that you have to be able to adjust these catalysts that include changing the composition of, say, of a metal nanoparticle, changing the size, and then changing the supports. And so this is actually a lot of knobs, and so you don't want to be changing a material and then just letting it go react and hoping to come back and look at it later and have some hope that it wasn't really modified. And so this ability, I think, is really critical for making fast progress. And so I think a really beautiful example of this is some of the work that's coming out of Scott, that actually Scott Anderson published in Science a couple of years ago. And as I said, he's doing this kind of experiment where he's in the gas phase preparing clusters, mass selecting them, and then landing them on a surface of TiO2, and then reacting them, looking at CO oxidation, and correlating this on a sort of cluster size, sequential cluster size basis with the electronic properties that he's measuring by XPS. And so this is really a nice study that you can really see there's a non-monotonic sort of dependence of how the activity in terms of the reaction goes, and it's tracked very well by the electronic structures. And so this is, I think, very, very nice work. And so there are theorists going after being able to predict this behavior as well. And so another example of this is some of the work that Stefan Veit is doing in collaboration with the Pfefferle group at Yale. And here they're doing a similar kind of thing. This is an example where the program is doing work that's taking advantage of some of the larger laser facilities. This is doing grazing incidence, small angle X-ray scattering and X-ray absorption in combination with temperature program reactions. And again, they're taking size-selected particles and they're characterizing them both with X-ray and then doing reactions on the spot. And here are the results they see. This is for cobalt on magnesium oxide. And what they can do is characterize the particle size as they're heating up these particles. And what they see is that when you get up to about 300 degrees, they see the most activity. And the other thing they see here that sort of you wouldn't really expect is that the particle size changes and narrows. And then when they cool it down again, it broadens out. And so we'll have to see if this, just the ability to really go in and see reactions and the size dependence, I think, is really a breakthrough. So now I'm going to move on to talk about some of the programs that are in Mike's core. The first one I'm going to talk about is some of the work that Mike Fair is doing at Stanford. Mike is a leader when it comes to doing developing. He's a world leader in terms of developing two-dimensional infrared spectroscopy. In fact, he got the Shallow Prize from APS this year for the success he's had in that area. And this is some of the work that he's been doing that's taking advantage of some of the techniques that he's demonstrated in homogeneous systems, or at least in solution. Some of those are also heterogeneous, but not really on solid surfaces, where instead of just doing simple pump probe spectroscopy, you can do more complicated techniques. These are four-wave mixing studies, kind of like the CAR studies that Rick was talking about. But these are using IR pulses, and so then you can get an IR vibrational echo, and if you monitor it as a function of the pump and probe frequency and analyze it, you can learn things about the structural dynamics. So these are actually distinguishable then from just the energy relaxation dynamics that you would see in a pump probe system. And he's used this to investigate this tricarbonyl rhenium that's attached to a surface. And what he sees is that you get the fastest relaxation. This is a structural relaxation in solution because of it interacting with the solvent molecules. When you put it on the surface, it slows down a little bit when the solvent is still there. And then if you take the solvent away, these structural fluctuations actually are relaxed the most slowly. So one of the things that's interesting about this is that he also did the pump probe studies to look at the energy relaxation, and it actually has the opposite trend. When it's on the surface, it relaxes the fastest. So now you're able to go in and look at some of the real details about different kinds of motions and relaxations, and then we can see what happens and see what are the kinds of motions and relaxations that are going to mediate either reactions or other kinds of properties, because you're getting a more detailed look at what's happening in these systems. So some of the programs in this portfolio are exploiting plasmon interactions. We saw a lot of that from Gernot's talk, and there's a lot of work on metamaterials in AFOSR. And as I mentioned, while there was some early work funded in this program by Mike, really looking at sensors. A lot of plasmon interactions allow you to do SIRS with a lot more sensitivity. And so there's a lot of sensing capabilities. You can do enhanced IR absorption as well. But now things, I think, are migrating towards really trying to promote reactions. And so this is an example of some of the work that's being done by Peidong Yang at Berkeley, where he's demonstrated that if you take sort of a structured gold surface that's got some plasmonic effects and then put a coating of iron oxide as a photoanode, he gets enhanced current when you expose this to sunlight. And this is mostly due to that you get improved absorption due to the plasmonic of the structured metal, as well as some photonic effects in the structured substrate. And so this is very useful for being able to enhance these kinds of processes and make them more efficient. So another plasmon-related project is one that's reported in Science by Naomi Hallis. This is one in which what she's done is to fabricate gold nanobars on top of doped silicon. And so there you've got a Schottky diode, and this gives you sort of an antenna diode structure. And what this allows you to do is to be able to use absorption of the plasmon bands that then tunnel across the barrier. And now you can change the size of the nanobars, and this gives you sort of tunability. But one of the nice things about this is now, compared to using a semiconductor for a detector, you've decoupled sort of the constraints of the band gap on what photons can be absorbed, because you can change this barrier and basically make it what you want. And so when it comes to solar harvesting, a lot of the problems is that the semiconductors that are efficient for doing reactions are ones that have large band gaps. And actually, Martin Moskowitz wrote a perspective in Science on this article and pointed out that this may really be a game changer in terms of being able to overcome that limitation of decoupling what the bandwidth is for the absorption and the kind of material that you can do for something that you want to do with hot electrons, whether it's as a detector or for some other activated process. So next I'm going to talk about a couple projects that really point towards a direction that I think Mike is intending to go with this project, which is to develop expanded capabilities for catalysts. This could be coming up with more elaborate structures that you can take monomeric units and put them together in unique ways, as well as doing things sequentially or activating catalysts. And here, some of the things that leap to mind are using fields or maybe photons. And this could, some of the work, I've had discussions with John Lucasland talking about some of the microplasmas as being ways that you can augment otherwise static catalysts to a great effect. So one example of being able to use a field to mediate material processes is some of the results that was reported by Ken Knappesberger from Florida State University. He's actually a YIP. And he's been able to demonstrate that by applying a magnetic field, he can alter the fluorescence yield in these cadmium selenide nanorods. And he can sort of understand this because it sort of modifies the recombination dynamics. And this is sort of an example how you might be able to actuate something that could be catalytic. Other ideas that you can get that are that you might be able to feed from is there's a lot of switching projects that are going on in RSE as well. Another example of this of being able to get something that's a little more active is a project that Sen is carrying out at Penn State. And so he's fabricating these two-sided Janus particles where one side is gold and the other one is silica with a Grubbs polymer catalyst. And so what he's been able to observe is that when you put these in gradients, the particles move around. Or if you, or they tend to have larger diffusion coefficients as you increase the concentration. And this is looks like chemotaxis, which is basically that you've got particles that are migrating towards a gradient. And so this is a way that you might be able to engineer particles to give you motion and get them to go towards a specific site and maybe have some effect to be able to remediate some catalyst. So Another area that's being looked at is energetics. So in this area, there's a lot of work, several projects that are looking at ionic liquids, and a group that I think Mike basically sort of shepherded together is one that combines Robin Rogers, who's a very prominent ionic liquid researcher, with Scott Anderson's group, and there's also involvement with the folks at Edwards, Jerry Boats, Stephen Snyder, and Tommy Hawkins. And so what they're able to demonstrate is really a very convenient and effective way to be able to mill boron nanoparticles as an additive for energetic material. And this is something that they've been able to demonstrate that really scales very easily. It kind of skips some steps of being able to mill it in something and then sort of substitute out the solution. And these formulations give you long ignition times without much delay. And they actually have a paper that's coming out now in Chem Communications, and they're actually doing research to really understand the mechanism behind getting this to work. And so initially they were trying this with this BMIM, butylmethylimidazolium ionic liquid with a dicyanamide, but more recently they found that there's another cation, which is monoamine triazole, that works even better. And so they're doing studies to be able to understand what it is that's really getting this to work. So another project that's also a collaboration between university and AFRL is one in which they're using, between Steve Leone and the AFRL, Jerry Boats and others, is a work in which they're characterizing gas phase ion pairs of ionic liquids using VUV time of flight mass spectrometry at the advanced light source. And one of the nice things that they've been able to do is to demonstrate that if you use an aerosol source rather than an effusive source, you get sort of a gentler production, lower energy. And what that translates into is that you're going to get higher sensitivity, but you've also got more selectivity. You know, if you can make everything in sort of a lower energy state, you're going to get better resolution. And you can sort of identify this from the onset for the photoionization from the two different sources. And that also gives them a better opportunity to look at things like the emim bromine decomposition that they've been looking at, and that Jerry's actually been doing, Jerry Boats has been doing calculations to understand. So finally, let me summarize. You know, this program is using chemical physics and physical chemistry techniques, theory, and experiment to really get a detailed look at what's happening in terms of catalysis, to really understand that and improve the materials. These are very important for DoD, especially when it comes to improving power and energy generation and utilization. This is using and developing state-of-the-art methods to do this, where a key here is to be able to look at what's happening in increasingly more realistic systems to be able to understand the mechanisms in order to be able to guide the development of better materials. And there are opportunities still in terms of the fuel production and trying to improve these techniques. So thank you very much.
We have time for questions or comments. You?
I didn't realize the ionic liquids can stabilize boron nanoparticles. So do they know the mechanism of how that's being accomplished?
Of the, well...
Of the ionic liquids stabilizing it?
Well, one thing they do know is they're using XPS to look at what it is that's capping the metals. And I should have said they're doing it with more than just boron, too. And you know, they're just
other nanoparticles? Other nanoparticles?
Yes, other materials besides boron. So you know, aluminum also is working, and you know, they're getting particles that really you can ball mill down to microns with other kind of liquids. I think even organic liquids, but I think they're finding that these really are very small. They're capped. They're very stable, and they're doing. You know, they're basically finding that the ionic liquids are doing a good job of capping them.